Did you know that one mistake could cost millions of lives? In this story, the USA decided the fate of the war in just a few days. If you're interested in the truth about World War II, subscribe and hit the like button. There are many shocking facts ahead. February 8, 1942, Yogyakarta Airfield, Java. Imagine standing on the edge of a sun-struck runway as a Boeing B17 Flying Fortress, serial number 412471, sits forsaken on the tropical field, its American crew having slipped away only hours before the advancing Japanese. This machine belonged to the 7th Bomb Group of the United States Army Air Forces, battered by a crash landing yet, in essence, still whole. Within days, Japanese troops would come upon this bomber and others like it, strewn across the newly seized airfields of Java. What secrets lay inside its aluminum skin? What would an enemy learn by peeling back its panels and tracing its cables? Very quickly, the B-17 ceased to be merely a piece of military hardware. It became a manifesto in metal, an entire manufacturing philosophy rendered in rivets and wiring, one that clashed sharply with Japanese production habits. Over the next 3 years, Japanese engineers would pore over captured flying fortresses, cataloging every bracket and bulkhead. The judgments they formed would strike at their own confidence, undermining the belief that Japan could ever rival the torrent of American industrial output. The trail of discovery took shape in March 1942 as the conquest of the Dutch East Indies reached its conclusion. At Madione Field in Java, investigators found B-17 412471 in unexpectedly sound condition, though the nose section and engines were gone. Nearby airstrips offered more, additional B-17s in varying states of ruin, like chapters torn from the same book. Terao Saito, an aviation editor with Asahi Press who toured the newly occupied bases almost immediately, recorded what he saw. He counted 4 B-17Es being readied for evaluation, one at Malang, another at Cirebon, and 2 at Bandung. The maintenance arrangements for the B-17 in Java, Saito later observed, were excellent considering the time and the conditions. It appeared that Bandung Field had served as the Americans' primary maintenance hub, and it was there that technicians from GIKEN undertook their first assessments. Would you, in their place, not have been eager to open every access panel and ask what this airframe could teach? GIKEN, the Koku Gijutsu Kenkyujo, or Air Technical Research Institute, stood at the apex of Japanese aeronautical science. Based at Tachikawa Airfield near Tokyo, it gathered the country's most accomplished designers and engineers under one roof. Once word reached Tokyo that intact B-17 bombers had been taken, GIKEN moved at once, dispatching technical teams to Java. The message was unmistakable: examine, understand, learn. Yet the task was formidable. The B-17E represented the most advanced American model then flying in the Pacific. Its systems, a labyrinth more intricate than anything in the Japanese inventory. Using parts salvaged from several wrecked fortresses and enlisting captured Allied mechanics pressed into service, Japanese engineers set about the meticulous work of returning at least 2 B-17Es to the sky. It took months. They had to master electrical circuits, hydraulic runs, and engine installations that diverged fundamentally from familiar Japanese patterns. They studied instruction manuals found with the aircraft, translating the technical language and absorbing American engineering practice line by line. By late 1942, their persistence paid off. 2 B-17Es were airworthy again, ready to yield lessons that would test Japan's assumptions about the American way of making war. A third aircraft, this time a B-17D seized at Clark Field in the Philippines, had already been ferried to Japan earlier in the year. With that precedent set, the decision followed. The newly restored Java B-17Es would also be sent to Japan for a thorough, ground-up evaluation. Picture the planning room, maps unrolled across a table, pencils tracing a thin path from Java through Singapore and then north toward the home islands, a journey of thousands of miles over territories only recently taken. How do you move enemy bombers through friendly skies without risking a fatal mistake? The answer was elaborate choreography. Detailed flight plans were drafted so meticulously that not a single gun battery along the route would be caught by surprise. Fighter escorts were assigned. Hovering nearby would be a Nakajima L-2D transport, Japan's license-built Douglas DC-3 serving as a kind of airborne shepherd. Every air defense unit along the corridor received advance notice. Imagine being the officer reading that dispatch. Do not fire, these flying fortresses are ours. In May or June 1943, after this careful orchestration, the two B-17Es touched down safely at Tachikawa Airfield near Tokyo, joining the B-17D that had arrived from the Philippines earlier in the year. Now, gathered in one place, stood three examples of America's principal Heavy Bomber 3 metal textbooks waiting to be read. Major Kazuyuki Saito of the Imperial Japanese Army Air Force took command of the project at Tachikawa. An aeronautical engineer seasoned in design and testing, he assembled a cadre tuned for total comprehension. His team included Lieutenant Shioyama, Lieutenant Second Class Kurusu and Ohara, and Army Assistant Engineer Shimamura. Major Uno and Captain Yagi assumed the roles of test pilots, while Army Engineer Kaneko focused on engines and propulsion, preparing to peel back the secrets of the bomber's beating heart. Ask yourself, if you were in Saito's position, what would you examine first? The bones, the nerves, or the muscles of this machine? Their mandate admitted no half measures, record every facet of the B-17's design, construction, and performance. Because complete instruction manuals had also been captured, the team could match every physical component to an official description. The plan was exhaustive: test each system, inspect each component, analyze each manufacturing technique. Every rivet line became a sentence, every wire run a paragraph, the whole airframe a meticulously authored book. They began with the structure. Engineers measured rivet spacing, checked panel thicknesses, and noted the dimensions of spars and frames with almost ritual care. What surfaced immediately upended prior assumptions. Across all three aircraft, the consistency was uncanny. Rivet holes lined up from one bomber to another. Structural members appeared interchangeable. The contour and forming of panels showed the same signature across multiple airframes. This was not the handiwork of individual craftsmen trimming and fitting parts to a single airplane. This was mass production, systematic, standardized, and governed by precise tolerances. Here, the contrast with Japanese practice stood in sharp relief. Japanese aircraft production leaned on highly skilled artisans who individually fitted components to each airframe, which meant no two airplanes were perfectly alike. A part taken from one machine often required reworking before it would fit another. Field repairs demanded technicians capable of reshaping replacements to the particular quirks of the aircraft in front of them. Picture a mechanic under a tin roof shelter, filing and drilling to make a panel just right. The Americans had taken a different road. The B-17 suggested a philosophy in which any properly manufactured component would mate to any aircraft of the same model straight from the crate with no need for hand fitting. That level of standardization implied a manufacturing precision Japanese factories had not yet reached. It was as if the Americans had replaced the artisan's bench with an orchestra of gauges, jigs, and fixtures, every note struck the same way every time. Then came the engines, and the lesson grew louder. The Wright R-1820 Cyclone radials that powered the B-17 were assemblies of hundreds of exactly machined parts. The team broke the engines down completely, gauging clearances, logging tolerances, and comparing pieces from one power plant to another. The findings were startling. Components were machined to tolerances measured in thousandths of an inch. Crankshafts, connecting rods, cylinder barrels, pistons, part after part, showed virtually identical dimensions across different engines. The maintenance manuals validated what the micrometers had already told them. American mechanics in the field were expected to swap major engine components without special fitting. A cylinder from one engine could be installed directly in another of the same type. A crankshaft was a crankshaft precisely interchangeable so long as the model matched. Set this alongside Japanese engine production, where fitting and adjustment were the norm, and the contrast could not be starker. If you were an engineer reading those numbers, would you not feel the ground shift beneath your feet, sensing how industrial method could become a weapon as decisive as any bomb load? Japanese aircraft engines demanded the touch of seasoned hands. Components were hand-fitted, clearances coaxed into place by experience and feel. Field maintenance called for mechanics who could not only turn a wrench, but reshape, adjust, and improvise. The American method, by contrast, built the expertise into the parts themselves. Precision, born at the factory, so that the man on the flight line needed skill, yes, but not the artisan's intuition. Imagine opening an engine crate and knowing without hesitation that what lay inside would fit first time, every time. How would that change the tempo of war? The hydraulic system told the same tale in a different language. Japanese engineers traced actuators, valves, and controls across the airframe, noting how fittings used standardized threads and lines met with identical couplings from nose to tail. Any unit could be pulled and swapped without trimming or filing. No peculiarities, no, this one is different. What does it do to your confidence when the machine answers with uniformity instead of surprises? Then came the electrics, revealing an even more rigorous standardization. Every connection terminated in a machine-crimped fitting rather than a solder joint crafted by hand. Wire gauges followed consistent conventions from one panel to the next. Circuit breakers, switches, and instruments presented themselves as modular blocks: remove, replace, restore. Where Japanese aircraft wiring typically relied on skilled electricians able to solder, adjust contacts, and untangle bespoke circuits, the B-17's electrical heart was designed so that a basically trained mechanic could swap entire assemblies using simple tools. Picture yourself under a wing with a toolbox. Wouldn't you rather trade a suspect bundle for a fresh one than chase a fickle solder joint through a maze? Even the crew's oxygen system spoke of this philosophy. Precision regulators allotted flow to each position, and here the revelation was almost unsettling. Manufacturer stamps showed these regulators came from automobile parts suppliers, firms with no prior aircraft pedigree. Consider the implication. American industry was so broad and so disciplined that car part makers could pivot to precision aviation hardware simply by applying their manufacturing habits to a new catalog. What does an adversary do when his rival can summon entire sectors to build instruments as effortlessly as they once built axles? The bomb release gear delivered the same message in steel. Japanese racks often required meticulous tuning by armament specialists. In the B-17, the shackles were self-adjusting mechanical devices, no calibration rituals, no delicate dance. Pull the lever. The system behaves as promised. Defensive armament left a particular impression on Japanese fighter pilots who flew practice intercepts against the captured fortresses. 13 Browning M250 caliber machine guns formed overlapping fields of fire that guarded nearly every avenue of approach, each weapon capable of up to 600 rounds per minute. And the guns themselves revealed another facet of American thinking. To Japanese engineers accustomed to aircraft weapons built with exquisite tight tolerances, the Brownings looked almost crude manufactured to comparatively loose fits. Yet they ran. Reliability flowed not from fussy craftsmanship, but from robust, forgiving design. Any competent armorer could keep them working with basic training and a modest kit. If Japanese aircraft guns were precision instruments requiring careful upkeep, American guns were rugged mechanisms meant to function amid dust, cold, and hurry. By autumn 1943, all 3 captured B-17s were flying regularly out of Fusa Airfield near Tachikawa, giving Japanese pilots first-hand time at the controls of a heavy bomber. Test sorties logged performance figures, handling notes, and operating procedures. The aircraft soon appeared in Japanese military training films that illustrated tactics for intercepting American heavies. In these reels, Ki-43 and Ki-44 fighters practiced attacks against the captured B-17s. At times, the B-17D even reappeared in American markings, occasionally escorted by a captured Curtiss P-40 to heighten the illusion. The same films played in public theaters as propaganda, showcasing Japanese fighters engaging American bombers with apparent success. But the camera did not capture the conclusion etched into pilots' logbooks after repeated practice. Even when an attack went well, the B-17's defensive firepower and sturdy structure made it a daunting quarry. More unsettling was the stark arithmetic. For every B-17 destroyed, American factories would deliver replacements faster than Japanese industry could replace its lost fighters. Can you feel the weight of that realization the moment when strategy becomes a production schedule? Earlier that year, in February 1943, Asahi Press issued a comprehensive volume titled Anatomy of the Enemy's Aircraft. Its pages offered a deep examination of captured Allied types with special emphasis on the B-17, photographs of every major assembly, technical drawings of critical systems, and line after line of specifications. The book soon became required reading for Japanese aircraft engineers. Open it, and you could trace the entire philosophy system by system, part by part, of a machine that taught as much about industrial capacity as it did about war in the air. Mitsubishi engineer Hisanojo Ozawa, the mind behind the twin-engine Ki-21 and Ki-67 bombers, contributed an assessment of the B-17 to the May 1942 issue of Koku Asahi, Asahi's aviation magazine. His reading of the fortress was revealing both in what it openly conceded and in what it sidestepped. Ozawa pointed out that the B-17E was, at heart, an evolution of a design first flown in 1935, implying that its foundations were rooted in an earlier era. He noted that Martin B-10s and Handley Page Hayfords of comparable vintage had already disappeared from frontline service, and yet, he admitted, progressive refinements had lifted the B-17 into a first-line combat role, and the original concept, he allowed, had been exceptionally sound. Do you hear the undertone? Respect without surrender, acknowledgement without fully naming the threat. Another authority, Shizuo Kikuhara, the designer of the four-engine Kawanishi H-8K flying boat, studied the captured B-17s and singled out what impressed him most. The American engineers have perfected the subsystems of this bomber to such a degree that a minimum of controls are needed in the cockpit, he wrote. That very simplicity, given the aircraft's size, signaled a high level of systems integration. Imagine sitting in that cockpit. Fewer levers to manage, fewer switches to hunt for order rather than clutter, intent rather than improvisation. What these published analyses carefully refrained from stating outright was the most unsettling conclusion of all. The B-17's construction methods showcased an industrial organization that Japanese factories could not equal. The fortress did not dominate because it possessed superior aerodynamics or overwhelmingly more powerful engines. It dominated because American industry could build it in numbers that would swamp Japanese air defenses by sheer volume. Ask yourself, if a rival can make 3 while you repair 1, how long can skill alone hold the line? The teardown revealed the B-17's fabric in exacting detail. Wing panels were stamped from dies, not laboriously hand-formed over wooden blocks. Such stamping demanded massive hydraulic presses and precision dies that cost small fortunes to create. But once those dies existed, panels could be turned out by the hundreds each day. Control surfaces told the same story of master tooling. Ailerons, elevators, rudder sections. Each bore the unmistakable mark of identical forming, rather than the touch of individual craftsmen. The main wing spares, those critical members that carried flight loads, were machined on automated equipment. Drill patterns matched exactly from one airframe to the next. Any wing rib taken from one fortress would seat precisely in another of the same model. The landing gear, too, proclaimed automation and precision. Main struts forged, heat-treated, and then machined on automated lathes. Actuating mechanisms built from hardened parts held to identical specifications. Picture an assembly line where jigs, not hammers, dictate the fit, where the machine remembers so the worker doesn't have to. In early 1944, a ground accident furnished an unexpected chance to cut deeper. During takeoff from Fusa Airfield, a captured B-17E was caught by a sudden crosswind. Its right wing struck a parked Ki-49 bomber. Both aircraft were destroyed. Tragedy became opportunity. Engineers could perform a destructive examination, slicing into the wing to study construction hidden from view on intact machines. By opening skin and structure, they could measure how the rivets had truly been set. They measured hundreds. The results were stark. Rivet diameter varied by less than 0.02 of an inch. Installation depth deviated by less than 1/10,000th of an inch. Such uniformity across thousands upon thousands of fasteners simply could not be achieved by hand riveting. The conclusion was inescapable. The airframe had been assembled with automated or semi-automated riveting equipment. Do numbers ever feel louder than words? Here, the micrometer spoke in a voice no rhetoric could drown out. And the implications reached far beyond one dismantled wing. If American factories could build a B-17 with this degree of consistency, they could build them quickly. If parts were truly interchangeable, field maintenance became radically simpler. If precision lived in tooling rather than in individual craftsmen, production could expand its speed by training new workers, not by finding more masters. Consider the battlefield arithmetic that follows. When standardization becomes your ally, time and scale do your fighting for you. Japanese aircraft production lived under a very different star. Skilled craftsmen were scarce, and producing more of them was a matter of years, not months. To increase output, one could not simply install more benches on the line. One had to discover and then train additional masters. Imagine being a factory manager told to double production. Where would you find the hands to match the demand? Then came May 1945. American photographic reconnaissance over Tachikawa Airfield brought back frames that left intelligence officers frowning at their light tables. There, plain as day, sat what looked like a new Japanese four-engine bomber, or perhaps a transport. Analysts measured the images and put the wingspan at roughly 104 feet. The Phantom received a provisional designation, Tachikawa 104, named for its perceived span and location. As days turned into weeks without fresh information, speculation swelled. Had Japan managed to birth a new heavy aircraft despite the pounding of its factories from the air? Yet none of the analysts guessed the simple truth. The mystery machine was one of their own, an American B-17E Flying Fortress still under Japanese evaluation 4 years after capture. The B-17's real wingspan, 103 feet 9 inches, made the American estimate eerily on target. For all the exhaustive study of the captured fortresses, the effect on Japanese bomber design proved modest. Japan tried to adapt the Douglas DC-4E transport into the Nakajima G5N bomber, while its other land-based four-engine type. The Nakajima G8N, entering production as the war neared its end, employed more advanced structural ideas that drew nothing from the B-17's airframe engineering, and yet traces of influence did surface in systems and components. Most notably, there were determined efforts to master turbo superchargers for high-altitude performance. Several advanced programs, the Army's Tachikawa Ki-74, Mitsubishi Ki-83, and Nakajima Ki-87, along with the Navy's G8N and Mitsubishi J2M, failed to realize their promise, chiefly because turbo supercharger technology would not settle into reliable service. The obstacle was not comprehension. Japanese engineers who dissected the fortress understood the principles. The obstacle was making. Turbo superchargers demanded high-temperature alloys and precision processes that Japanese industry could not reliably reproduce. Even when prototypes emerged, they faltered. The same manufacturing constraints that blocked mass production of standardized B-17-style components also checked the advance of these engine technologies. If the factory cannot hold the tolerance, the sky withholds the altitude. By 1944, the accumulation of evidence from captured American aircraft had led thoughtful Japanese engineers to somber arithmetic about relative capacity. U.S. production in 1944 reached 96,000 aircraft. Japan labored to produce 28,000, but even that stark ratio underplayed the chasm. American airplanes were assemblies of thousands of precisely made, interchangeable parts. Basic trained mechanics could keep them flying with standardized spares. Field repairs were swift. Machines returned to duty quickly. Japanese aircraft, crafted by hand, demanded skilled technicians, specialized replacements, and constant adjustment just to remain operational. Each American airframe therefore embodied greater practical combat power because it could be sustained with less effort and fewer scarce experts. Can you feel how logistics turns into strategy, how maintenance becomes a multiplier? The production system behind that advantage stood revealed in the B-17's very bones. Boeing's Plant 2 in Seattle had turned out 6,181 B-17s by the time production ended in April 1945. At peak tempo, 16 complete B-17s rolled off the line each day. Douglas Aircraft in Long Beach produced 3,000 B-17s between July 1942 and July 1945. Lockheed Vega in Burbank built 2,150 B-17s between August 1942 and August 1945. In total, the three manufacturers delivered 12,000 out of 931 B-17s. The Japanese engineers poring over captured fortresses in 1943 and 1944 did not possess these figures, yet serial numbers and construction dates stamped into components allowed them to infer production rates. The math was merciless. If American factories could build B-17s with such consistency, they could build them fast. If heavy bombers could be produced at that speed, fighters and other types would be pouring from the lines in even greater proportion. Japan had stepped into a war of industrial attrition against an opponent wielding 10 to 20 times its manufacturing strength. When the strategic bombing campaign against Japan's aircraft industry intensified in 1944, whatever hope remained of closing the gap disappeared. Boeing B-29, super fortresses, the B-17's larger, more advanced air soon, ranged over Japan in formations that Japanese defenses could not break. Each raid shaved away production capacity that could not be rebuilt in time. The Nakajima plant at Musashino, Mitsubishi's facilities at Nagoya, the Kawasaki factories, one after another, they absorbed the bite of precision bombing. Then, in January 1945, an earthquake struck and further fractured Mitsubishi's supplier network. Bombs from above and tremors from below. Together, they buckled Japan's aircraft output. By early 1945, monthly production had slid from more than 2,500 airframes in May 1944 to barely hold on at 500, and the downward slope continued through the war's closing months. If you were a planner staring at those figures, what hope would you pencil into the margins? After Japan's surrender in August 1945, the United States Strategic Bombing Survey fanned out across the archipelago to take stock. Teams of American engineers walked the floors of aircraft plants, clipboards in hand, recording methods and judging capability. What they saw aligned with what perceptive Japanese engineers had already inferred from their study of captured B-17s. Japanese aircraft production still leaned heavily on skilled manual labor. Standardization was limited. Interchangeability in many shops remained an aspiration more than a fact. Subcontractors delivered parts, but quality control and dimensional consistency often wavered. At Mitsubishi's Nagoya works, American visitors watched craftsmen hand-form aluminum panels that, in the United States, would have been stamped in dies. Manual riveting predominated where American factories relied on automated riveters. Individual fitting and adjustment were routine, where American assembly lines used precisely manufactured, interchangeable parts. The survey's verdict was blunt. Japanese factories were organized to produce hundreds of aircraft. American factories were organized to produce hundreds of thousands. No degree of determination or artisanal skill could bridge that structural divide. Would you ask a single workshop to outpace an entire system? The captured B-17s examined at Tachikawa between 1943 and 1945 did not survive the war's end. Some fell to American bombing. Others were likely destroyed by Japanese authorities to erase evidence. Yet the lessons they carried did not burn. They lived on in the minds of the engineers who had studied every rivet and rack. In the decades that followed, Japanese industry undertook a transformation deeper than anything attempted during wartime. The engineers who had cataloged American aircraft and documented American production methods brought those insights to the work of national reconstruction. They understood that parity with American capability required more than copying American products. It required adopting American production systems. That metamorphosis took 20 years. Factories that had depended on master craftsmen reorganized around precision machinery and automated processes. Industries that once prized individual craftsmanship learned to prize systematic efficiency. Manufacturing evolved from collections of skilled hands into integrated production systems. By the mid-1960s, Japanese plants were turning out automobiles and electronics using automated methods comparable to those in the United States. By the 1970s, they had refined the approach developing systems, such as Toyota's just-in-time manufacturing, that improved upon American mass production techniques. The craftsmen remained valued, but their mandate changed. Instead of shaping each product, they designed the production systems and tooling that allowed less skilled workers to build precisely made goods at scale. The precision that once resided in a craftsman's touch now resided in jigs, gauges, and equipment. Companies like Toyota, Sony, and Honda rose to global leadership by marrying Japanese attention to detail with American-style systematic production. The famed quality of Japanese products emerged from processes designed to build quality in, rather than from artisans laboring to add it at the end. Can you see how the locus of excellence shifts from the bench to the blueprint? By the 1980s, when American manufacturers were straining under competition from Japanese imports, American engineers crossed the Pacific to study efficiency on Japanese shop floors. The irony was plain to anyone who remembered those wartime dissections of American aircraft. In Japanese engineering schools, the tale of the captured B-17s became a case study proof that studying an adversary's products can reveal the skeleton of their industrial organization. It taught that success demands understanding not only what a rival makes, but how they make it. The B-17s had driven home a hard truth. Modern industrial warfare is decided not by superior craftsmanship, but by superior production systems. Not by building a few better airplanes, but by building adequate airplanes in overwhelming numbers. Not by relying on rare masters, but by creating systematic processes that let ordinary workers produce precisely manufactured equipment, rapidly and reliably. Those lessons won through the careful dissection of enemy equipment in wartime became the bedrock of Japan's post-war industrial ascent. The shift from craft-centered production to systematic mass production marked the final triumph of the principles embodied by those captured B-17s, scrutinized at Tachikawa. The very engineers who, in 1943 and 1944, had measured rivets and cataloged production methods emerged as the architects of Japan's industrial rebirth. By studying aluminum and machinery, they grasped a hard truth. Modern industry belongs not to those who boast the most skilled hands, but to those who command the most effective production systems. Imagine standing in their shoes. Would you copy a shape or decode the system that makes that shape inevitable? In manufacturing engineering classrooms today, the tale endures as a case study in seeing the invisible. By examining competitors' products, students learn to read beyond the artifact to the systems and methods that produced it. The lesson is pointed. Understanding an opponent's methods matters more than tracing their lines. Again and again, the story shows that the logic of production, not the elegance of a blueprint, ultimately decides who prevails in industrial contests. The Boeing B-17 Flying Fortress dropped 640,000 tons of bombs during World War II, earning its place among history's most effective heavy bombers through operations in every theater. Yet perhaps its most consequential legacy was not counted in sorties flown, but in insights gathered when Japanese engineers examined captured examples. They discovered that American industrial power flowed less from superior materials or sleeker designs than from superior organization of the manufacturing process. Standardization, precision tooling, interchangeable parts, and systematic production methods could achieve what craftsmanship alone could not. The rapid creation of complex machines in quantities limited only by available resources. Ask yourself, which is the greater weapon, the airplane, or the system that can replace it faster than it can be destroyed? The captured B-17s evaluated at Tachikawa are gone, destroyed more than 70 years ago. But their lessons reshaped Japanese industry and radiated outward to influence manufacturing worldwide. Engineers and manufacturers across the globe came to see that mass production and quality are not adversaries. They are complementary attributes of properly organized industrial systems. Quality, in this view, is not an afterthought added by gifted hands. It is an outcome designed into the process itself. And so, the narrative that began in February 1942 on a muddy airstrip in Java with a damaged Boeing B-17I awaiting capture by advancing Japanese forces concluded decades later with Japan and America standing as partners in advancing manufacturing technology. The examination of those captured bombers had taught Japanese engineers that their defeat had been inevitable. More importantly, it explained why. In understanding the why, they learned how to ensure that industrial inadequacy would never again limit Japan's capabilities. The Boeing B-17 Flying Fortress became a teacher to its enemies, and they learned the lesson well.